All right, well, we are going to be learning today not about electricity, but about static electricity, or some people really don't like that term and they like instead to call it electrostatics. I can't read it right there for some reason. But really, what's in a name? Oh, yay, fanfare. Okay, so I should start off giving credit where credit's due. So thank you to Shelley Gold Burgess of Avon Lake High School in Avon Lake, Ohio, for making this flip chart and then sharing it with the world, because I didn't have time to put my own together, but I did have time to kind of edit through there. So you'll be able to see as I go through this. This is what it looks like when somebody has more time than I do to put together these, because if you compare it to my others, there's lots of graphics and doodads that do different things like fanfare waves and whatnot. So thanks, Shelley, for being awesome at putting together flip charts. I did delete about half the pages. I only have 15 minutes to make this video. Okay, so electrostatics is the study of electricity at rest. So we're going to do this for just a little bit before you know what you can have fun with electrostatics, and you can do lots of important, amazing things, and like some of the concepts here are important as when we started talking about current electricity. But for the most part, the things that, you know, what does actual useful stuff in our day-to-day lives is current electricity. But again, it all like relates, not that electrostatics really is a separate thing. Okay, but we want to make sure you understand how charges work and everything before we talk about current electricity, so you kind of know more about what's going on there. Okay, so I'm not going to ask you that, you'll figure it out. And again, so objects have different charges because, remember, objects are made out of atoms, and atoms are made out of protons, neutrons, and electrons. The neutrons have no bearing on an object's charge since they have neutral charge. It's the protons and electrons. If you have more protons than electrons, you're positively charged. If you have more electrons and protons, then you are negatively charged. The rules of charges, okay? So if you have two things that are like each other, so if you're two alike, okay, in life, I guess, you repel, although that's not really true, but for charges it is. So two electrons, two negatives repel, two positives, two protons repel, okay? If you have opposites, opposites attract. Now, in real life, people like to say that. I don't think that usually works out quite the way people think it does. Oops, what's this? Okay. When we're talking about charge, just like charge is something in physics we can measure. If we can measure it, we need to have a unit. So the SI unit of charge is the Coulomb, and charge is symbolized with a Q. One electron has a charge of negative 1.6 times 10 to the negative 19th coulombs. One proton has the opposite charge of positive that same number. Okay. Again, just as I think I must have put back in the pages I thought I deleted. But here's Mr. Coulomb. Apparently he had, oh no, I left it in because I wanted to point out that we are told that he has very well-groomed eyebrows. Maybe that wasn't very common for people who lived back in the 1700s. Okay. So here's a problem that we could maybe try to work out at some point. How many electrons, how many unpaired protons must the bunny have? If it has, or sorry, how much charge does the bunny have if it has 2100 unpaired electrons? I'll leave that up to you. I think you can figure that out. Okay. So, the law of conservation of charge. Charge cannot be created nor destroyed. It can only merely be transferred. So if you start out with two neutral objects, like a bunny and a sheep, and you rub them together, and one will become positive and the other will become negative. We'll look at how do you tell in just a few moments. But if you take however much positive charge, let's say the sheep has, and however much negative charge the bunny has, and you add those two together, they're still going to sum to 0. Okay? So you cannot create or destroy charges, because you can't create or destroy electrons and protons just by like rubbing things together. Okay? So we ask the question, how do we know how much charge something has? And it's been determined, like experimentally, this thing called the triboelectric series. And the triboelectric series has to do with how much something wants to either gain or lose electrons. So on this list, it goes bunny fur, glass, wool, kitty fur, silk, cotton, wood, plastic, and sorry, down way at the bottom underneath plastic, and I actually cut it off on the bottom for the video. So down there it says metal. The further away things are on the triboelectric series, the more likely it is that they're going to get big charges. So if you rub some bunny fur with glass, the bunny fur will lose its electrons to the glass. So the glass will become negative and the fur will become positive. Okay, so the things up here are, since they're more likely to lose electrons, these things are more likely to be positive. Okay, and then down here, things are going to be more likely to be negative. Okay, down at the bottom end. So if you take a cat and you rub it, or sorry, where's wool? We're talking about the sheep and the bunny. If you rub a sheep and a bunny together, the sheep will gain the electrons, the bunny will lose it, and so you will get a positive bunny and a sheep negative. No wonder why those sheep always look so grumpy. Get it? I said that just for Wyatt. I think he'll appreciate that. Years from now, people will be watching this video because I haven't updated them, and they're like, who's Wyatt? Okay, when we're dealing with static electricity, and actually with current electricity too, things can be considered either conductors or insulators. If you are an insulator, that means you do not transfer electrons very easily. If you're a conductor, it means you do. They can both be charged. So, whoops, move. So there's two of them. Conductors are good for circuits. Insulators are good for protecting circuits from other things and from themselves. Conductors don't hold charge very well because if they touch something, it just kind of conducts it away. Whereas insulators hold charge much better because once you put it on there, it doesn't just go to the other side and leave out the bottom or whatever. It just kind of stays around. Okay, so there are different ways of charging objects. So I think the most kind of familiar way we have is when things come into contact by frictions, when they rub up against each other. So when that happens, objects transfer charge from one to the other. This can be done with either conductors or insulators. Again, it's harder to do with the conductor though. You can also charge things by induction. So if you bring a charged object near a conductor and then ground out that conductor. So what happens is if I have a charged, you'd think there'd be, okay, what just appeared? Oh, didn't mean to do that. Okay. So here we see a charged object is being brought near a electroscope. So if you touch the electroscope, you ground off the negative part, and then the electroscope is only left with the positives. So that now I've just charged that electroscope by induction. So even though I didn't actually touch, and see how it got the opposite charge of the object I brought nearby. You can also charge things by polarization. Okay, so if you bring a charged object near an insulator, okay, what happens is the electrons in the molecule themselves move to the other side. So water can be charged by polarization. Okay, so again, if we bring the charged object near the insulator, we can see we kind of like chase. Right now everything's all like neutral and happy, but then I bring the negative object nearby, and what happens is the positives stay close to that negative rod and the negatives get kind of chased away. So of course we're going to be doing some math with charge. When you're dealing with charge, we have what's called Coulombs Law. Coulombs Law is up in the top right box, and it's F equals KQ1 times Q2 over R squared. K is just a kind of a universal constant, which has the value of 9 times 10 to the 9th Newton meters squared per Coulomb squared. So you'll be practicing. That's a really important formula. Again, it's called Coulombs Law, and you'll be using that in class. Okay. You can draw parallels between gravity and electric force. The formulas for them, so gravity's on the left, electric force is on the right. You can see the formulas for them are very similar. Gravity is a very weak force. Electric force is much stronger. Just think about it like you rub a balloon on your head, you can stick it to the ceiling. So, the balloon is more powerful than the entire Earth. Gravity can only be attractive. Electric forces can attract or repel. They are both inversely related to the distance squared between the objects that are attracting or repelling in the case of electrostatic force. Whenever you have a charged object, it has an electric field around it. So when you look at stars, like it's not like a Star Wars force field, but physicists do call them force fields. And we can visualize these force fields, and we will be doing that in class. Okay, so there is an equation for determining the strength of an electric field, and the strength of the electric field is known as E. And so you use the same, basically it kind of looks just like Coulomb's Law, it's just missing some terms. And really that's all it is. So it's not really a special new formula. Okay? Can maybe work some problems out together later on. So we can diagram electric fields by the way of a diagram of an electric field works is what direction would a test charge go if it was placed near that. So if I have this negative balloon and I put it's always a positive test charge. So what I do is if I have a positive, is that trying to do anything? Okay. Oh, it gives me my force arrows. Okay. So no matter where I put ignore that arrow. No matter where I put my test charge, it's going to want to go towards the balloon. And so I put in arrows. And then when you're out further, the electric field is going to be weaker, and so I'll put in smaller arrows because they don't feel as much of a strength, and so on. So that's what diagramming electric field looks like, and again, we'll be doing that in class. Okay? And we can look at some different scenarios. Things can have potential energy. So just like they have a certain amount of gravitational potential energy based on where they are in a gravitational field, charged objects can have potential energy based on where they are in the electric field. And so the amount of potential energy something has because of an electric field is equal to it's the charge that's being acted on, the electric field strength, which is the E from the earlier equation, and how far you are from the object that is producing the field. We can also look at electric potential. So electric field strength is the amount of energy, whereas electric potential is how much energy you have per charge. So if you have twice as much charge, you recognize you have twice as much energy. And electric potential is in a unit that you've probably heard of before, the volt. Okay, and so 1 volt is equal to 1 joule per coulomb. If you break that all the way down into just base units, 1 volt is the same thing as 1 kilogram meter squared per second squared coulomb, which is a mouthful, which is why we just call it the volt. Okay, so this is where volt comes from. It's how much energy that each charge will have depending on the size of its charge. And again, it recognizes that if you have twice as much charge, you have twice as much energy. So if you can have something with a lot of charge and something with a little bit of charge, and they can have the same voltage, because it just means that the smaller one also has less energy. So you can talk about potential difference between two different places, which is just the differences in voltages between them. And so it gives some equations for those. So it's the potential energy divided by the charge that you're dealing with, or it's the electric field strength times the distance. Either one of those can give you the voltage. Okay. So here's just a nice summing up thing, and I'm just about at the end of my 15 minutes. I know that's kind of whirlwind, but that's why you have the notes to look back on. And you can pause video and refresh, and we'll discuss too.